So we're going to talk about the difference between conductors and insulators. So I'm not going to define these yet. I kind of want to rely on your knowledge. If I were to ask you, name some materials that are good conductors and name some materials that we use as insulation. And stop the video for a second and see if you could just jot down a couple of things that you think are good conductors and good insulators. All right, hopefully what you know from your own experience is things like metal or metals are good conductors. Some metals are better conductors than others. Specifically, you may have said something like copper, because we make wires out of copper. Wires inside of really important electrical devices are made out of gold and silver, specifically. Some other things that you might have said are conductors. Water is a conductor, specifically if the water has salt in it. Salt water is a very good conductor, but water itself can be a good conductor. So what are some things you might have said are insulators? Hopefully you said things like plastic and wood and glass. What other things like wood, plastic, glass? Something like maybe, I don't know, cloth or wool, etc. Right? So hopefully what you're seeing here remember from chemistry, some ideas that we have metals, and then we have here, these things tend to be nonmetals, right? So conductors versus insulators. And this comes from our experience of it. But what does it mean to be a conductor? What does it mean to be an insulator? So here we go. Let's define a conductor as a material. So it's not an object, it's what the object is made out of, the stuff. So it's a material that easily allows for the flow of electrons through it, right? And that's what the definition of a conductor is. And some things are better conductors than others. There is a way of mathematically describing how much better some things are conductors than others, but we're not really going to get into that. Then what's an insulator? Well, this is going to be a material that does not easily allow for the flow of electrons through it. Now, it should be noted that an insulator, the definition here is not that they don't allow. If you push electrons hard enough, no matter what type of material that you have, it will flow through. So why are metals good conductors and nonmetals not good conductors? Well, it has to do with their structure, and it has to do with something hopefully that you learned last year in chemistry. I know I've said that a couple of times already here. I'm going to say it a lot more in the coming week, right? It has to do with the concept that some elements hold on to their electrons much more strongly than others do. Do you remember what that's called? And if you remember the concept of electronegativity, that's what I'm talking about. So as you move to the top right-hand corner of the periodic table, you have materials that hold onto their electrons really strongly. And as you go to the bottom left-hand corner, you have things that give up electrons very easily. And then metals are also structured in a certain way. They have very loosely bound electrons, right? And these have very tightly bound electrons. Now, oftentimes with metals, we say that the structure of a metallic solid is something that is often called the sea of electrons, meaning that the electrons don't necessarily belong to any particular atom. They kind of float from object to object, and it all kind of net comes out in balance. Hopefully you heard about that in chemistry. So that's the difference between conductors and insulators. Now I want to say one other thing, draw another picture here to help you out. Let's say that I had a metal sphere. So this is a metal sphere. So it's a conductor. And here I have a plastic sphere, like like a rubber ball, right? And let's say that, I don't know how, but, or actually let's just say that each of these things is initially neutral. So what does it mean that they're neutral? It means not that there are no positives or negatives. It means that there's an equal number of positives and negatives. For every proton that makes up this metal, there's an electron partner such that together they're net neutral. Same thing with the plastic. For every proton, there's an electron. Let's say I add a couple of extra electrons. So let's say I'll put them here, 1, 2, 3, 4. And I do the same thing with the plastic. Now we're not going to talk about how we got those extra electrons on there. Let's say they came from somewhere else and they ended up on this device, on this sphere. So over time, what would happen? Well, here's the thing. These electrons, because they're all negative, are repelling each other, right? And so what's going to happen is that the electrons on this thing are all experiencing that extra repulsion beyond the electrons that are already there. Because the metal, they're free to move, what's going to happen is that the electrons are going to move around to minimize that repulsion. And so they end up kind of distributed along the outside as equally as possible, right? Because that distribution minimizes the repulsion between these. Whereas for the plastic over time, because plastic is an insulator, unless there's a huge force of repulsion there, there's no reason why those electrons are going to move. They're going to kind of stay there because the atoms in this area are strongly holding on to the electrons, even though they're extra electrons. Okay? And so that's what happens with charge on a metal. On a metal object, excess charge distributes on the outermost surface to minimize forces, okay? Whereas that's not going to happen here on the insulator because the charges are not free to move, okay? So that's going to have a couple of implications in terms of things that we're going to talk about this week.